Last section of chapter 6, 6.3, we are learning about binomial and geometric distributions. What is the only distribution we've talked about in this class so far? We've talked about the normal distribution a lot, right? We are now going to learn about the binomial distribution. The binomial distribution comes in handy when we are trying to do things, calculations, with a binomial random variable. So, what is a binomial random variable? It is a random variable. By the way, side note, what are the two types of random variables we have discussed in this chapter? Discrete and continuous. So discrete and continuous. What is a discrete random variable? It is a number that is countable. It's when I'm counting something, okay? I'm counting a number of something. What is a continuous random variable? What are we usually doing? Measuring something. Very good. Okay, back to this. A binomial random variable is a random variable, so it can be discrete or continuous, but most of the time, actually, that's a lie. It's going to be discrete, just saying. You'll see why in a minute. A binomial random variable is a random variable that, what does it do? Counts, there it is, that's why it's discrete, that counts the number of successes. That's going to be x in a fixed number of trials. And that's going to be n, your sample size, basically. A random variable that counts the number of successes, x, in a fixed number of trials, n. In order for something to be considered binomial, it has to meet four conditions, four different conditions. First of all, it has to be binary. Do you guys know what binary means? It means there's only two options. So in this situation, for something to be binomial, binary, it has to have success versus failure. There has to be a clearly defined success versus failure. So I'm going to take a random sample of 10 of you, and I am going to notate if you are wearing glasses. Is there success and failure? What is success? Glasses. What is failure? Not. I'm going to take a random sample of 10 of you, and I'm going to notate how many blondes there are. Is there clearly defined success and failure? What is success? What is failure? Not. I'm going to take a sample of 10 of you, and I'm going to notate the color of your shirt. Is that binary? I'm going to notate the color of your shirt. No. There's not a clearly defined success and failure there. What if I said, I'm going to take a sample of 10 of you, and I'm going to notate how many white shirts there are? Yes. That is good. Okay, cool. Do we understand the binary element? Independent. Do you guys remember how to test for independence? No. So, in order for something to be independent or to be binomial, it has to have independent trials. The trials are independent. Obviously, you guys, the most common things, rolling a die, that's independent. Every time you roll a die, it's independent. Flipping a coin, that's independent. Things like that. Picking, people out of a big population, each person is independent. Those are all going to be kind of things that you'll probably know are independent. Otherwise, it'll probably say it in the problem. It'll probably say these are independent events, okay? All right. Binary, clearly defined success and failure. Independent, trials are independent. N stands for number of trials is fixed. And that is going to be n, your sample size. How many times you're going to do this thing. So that has to be told to you up front. Before you even start, you have to decide, I'm going to pick 10 people. I'm going to roll the die 100 times. Whatever it is, you have a set number of trials. And then your success probability is fixed. And this is going to be a P for probability, okay? So, success probability is fixed. For example, if I'm rolling a die and I'm notating the number of ones that I get in 10 trials, what is the success probability? I'm notating the number of ones in 10 trials. When I roll a die, what's the success probability? 1 out of 6 every time, right? So when I roll a die on any trial, I have a 1 in 6 shot of getting a 1. So my success probability is the same every time I roll that die. It is 1/6, okay? This is how you check to see if something is binomial. To remember this, you can check bins. Bins. You're going to check bins anytime you are trying to see if something is binomial. If you find that it is in fact binomial, it is going to be defined by N and P, your sample size and your probability of success. Your number of trials and your probability of success. So we're going to check the bins. What does bins stand for?
Binary independent numbers.
It's not as fun, is it? Binary, there's success and failure. Independent trials, number of trials is fixed. Success probability is fixed as well. All right, cool. So that is binomial, and that's how you check to see if something is binomial. If I am counting the number of successes in n number of trials, how many successes might I get? I might get 0. Is it possible that I do something and I never get success? Yes. Okay, so there could be 0 probability or 0 success. Or N. Could it be that I do something and I get success every single time? It could happen. Okay, so for a binomial random variable, your X values will always go from 0 up to the number of trials with integers in between because we're counting. So it'll look like a discrete random variable. Bless you. The parameters, we've already talked about this. The parameters are N and P. So if you know that you have a binomial distribution because you check the bins, you would say that you have a binomial with N and P. And you would define what N and P is. Side note, I'm curious. Do you guys know what the parameters are that define the normal distribution? What are the parameters that define any particular normal distribution? That's what it goes from, negative infinity to positive infinity. But what defines a single normal distribution?
Just the amount of times things just n.
Not at n.
Just the amount of times something.
Anytime we draw a normal distribution, what do we always label?
Median.
The mean and the standard deviation. Every normal distribution has its own set of parameters, and it is mu and sigma. The normal distribution is defined by its mean and its standard deviation. A binomial distribution is defined by its number of trials and its probability of success. What do you guys think is the most common mistake that students are going to make on a binomial question? Mixing up the binomial and the normal. Basically not recognizing that it's binomial. So it's going to be not recognizing that it is binomial. So I'm going to give you guys a little tip. You are looking at a problem and you notice that it's asking you about probability. So if you have a probability question with no shape given and a set number of trials, you will probably need to go ahead and check the bins because it's probably going to end up being binomial. I'm not guaranteeing it, But if you are reading a question and it's talking to you about that you're going to do something a certain number of times, and then it says what's the probability of, and you look and there's no normal distribution mentioned, you will likely be doing a binomial problem. Okay, it's usually what that is. BINS, what does BINS stand for? Binary, meaning there's success and failure. Independent trials, number of trials is fixed, success probability is fixed. All right, let's see if you guys can figure out if something is binomial or not. We're going to roll a fair die, and we're going to let X be the number of sixes. Let's check the bins. B, is there a clearly defined success and failure here?
No. Yes, 6.
6 is the success. What is the failure? Not a 6. Okay, cool. So we have that. That's good. We got binary situation here. We got success and failure. I. What is I? Independent. Are these roles independent? Yes, always, right? So roles are independent. Cool. N. What does N stand for? Number of trials. Do I have a fixed number of trials? Yep, so N equals 10. Perfect. S. What does S stand for? Success probability is fixed. What is the probability of success here? 1 out of 6. So guess what? We have a binomial with the following parameters. N equals 10 and P equals 1/6. Whee! Wasn't that fun? Let's do it again. I'm not. We're going to do it again. The next one says shoot a basketball 20 times from various distances on the court, and we're going to let Y equal the number of shots made. Do we have a binary success and failure? Yes. What is success? Okay, what is failure?
Yes.
Yeah. Okay. I. When you shoot a basketball, is each shot independent of whether or not the other shots went in? Yes. Yeah. So our shots are independent. This is so fun. N. What's that stand for?
Number of trials.
Number of trials is fixed. Do I have a fixed number of trials? N equals 20. All right. S. What does S stand for? Success probability is fixed. Do I have a fixed success probability?
No.
Why not?
Depends on your skill.
What does it say? Various distances. Tyler, you play basketball. Is it easier to make a shot that you're closer to the basket than it is at half court?
Yes.
Of course. So your probability of making it changes depending on where you are on the court. So P is not fixed. Guess what that means about this situation, you guys? It is not binomial. Does that make it normal? No, it doesn't say anything about it being normal. It's just not binomial. It's not normal, so I don't know what the heck it is. It's just dumb. That's what it is. So guess what? I don't do anything with this. I don't do any binomial calculations. I don't do any normal calculations. I can't find this probability. Next. Observe the next 100 cards that go by and let C equal their color. Binary. Do I have a clear success and failure? No. I do not. So there is no clear success. So guess what? Not binomial. That's it. Why do I have to check the rest of it? If I know it's already not binomial, why would I do the rest of the work? That's stupid. Facts. All right, you guys, flip a coin 50 times. Let X equal the number of heads. Binary, do I have clear success and failure? Yeah. What is success? X. What is failure? Is each trial independent? Yeah. Okay. Flips are independent. Okay. N, the number of trials is fixed. Do I have a fixed number of trials? Yeah. All right, so N equals 50. And S, success probability is fixed. Yep. What is that? There you go. Probability is 0.5. So what do I have here? I have a binomial distribution with n equal to 50 and p equal to 0.5. How do you guys feel about bins? Pretty solid? This is pretty easy, right? Not too shabby. What do you guys think happens after you identify it as being binomial or not? Then you probably start doing some calculation with it, right?
Oh my gosh, Coach.
Are you ready to do some calculations?
Ms. Lakey.
Oh, you can call me. I'm coaching up stats. Let's go.
All these numbers.
Are we ready?
No.
Yeah, we are. Let's go.
Wait, so whenever like one of those steps don't work, you just stop.
You cannot use binomial. You cannot use normal unless it says it's normal. But if it says it's normal, you shouldn't be checking bins. Bins is like the backup plan to normal. Okay? Do not use bins if it says it's normal. That's silly. Okay? All right, cool. Okay, actually, what I just said, we'll talk more about that later this week, but for the most part, well, I'll go with that. All right, genetics. Let's talk about genetics. Genetics says that the genes children receive from their parents are independent, clue, from one child to another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 4 children. We are going to count the number of children with type O blood. Is this binomial? How do we check? Bins. Do we have a clearly defined success and failure? What is success? Child is born, check their blood, type O, success. Check their blood, type A, failure. Failure of a kid. How dare they? All right. I. Is each child's blood type independent of the other children? Yes. It literally says that, so yes. Cool. N, what does N stand for? Number of trials. Is it fixed?
Yeah.
How many?
4.
We had ourselves 4 children. All right. S, does it tell us the probability of success each time?
25.
Sure does. So P equals 0.25. So part B asks us, what are the parameters for this distribution? It is a binomial distribution with N equal to 4 and P equal to 0.25. Okay. Are you ready to do some calculations? Not yet. Well, yes, ma'am.
For I, can I just put blood type of each children, or do I have to put each?
Yeah, no, yeah, just that's
Can I
fine.
just write yes or no?
Yeah. No, you do have to say what you checked. So you checked that something was independent. What was independent? You can abbreviate independent as IND if you want.
But you don't have to clearly state independent. You can just put what it is. Like
Right.
blood type.
Each child's blood type. Yeah.
So when we don't tell you if it's independent,
Oh my
how can you tell?
Yeah. So that's a great question. The question is, if they don't tell you it's independent, how do you know it's independent? It would have to be something that you just intuitively know is independent, like rolling a die, flipping a coin, sampling from a large population. Like, you would just kind of know it's independent, or it has to tell you that it is. Otherwise, you can't assume it to be true. Usually, problems will tell you if they're independent or not, even if it says that you're flipping a coin or you're rolling a die or something like that. But for the most part, it's either going to be flipping a coin, rolling a die, or it'll say that it's independent. Yeah. Okay. Here we go. The best part of the day. We know how to check if something's binomial. Now, how do we calculate binomial probabilities? I'm so excited, you guys. Are you excited? Yeah! This is about to be so fun. This is highlight of my day right here. Here we go. I know what y'all are thinking. Sad day, lady. Whatever. It's fine. I got this. What is the probability that x equals 0? First of all, what does that mean?
No, then I have it.
There was 0 successes in these 4 children. What does that mean about their blood types?
All A.
All of them had a different blood type than type O. Here's what that actually means, you guys. That actually means that the first kid was born and was a failure. The second kid was born and was a failure. Then we had another failure and another failure. We got 4 failures on our hands. Okay? So here's how we calculate the probability. We are going to do the number of combinations. Basically, how many different ways can it happen that I have 4 kids that are failures, don't have type O blood? For this problem, there's only one way that happens. It's that they all fail, right? So there's really only one way here. Then here's what we're going to do. We're going to take the probability of success. Probability of success. And we're going to raise it to the power of the number of successes. Now, for this particular situation, what is our probability of success? 0.25. And how many successes do we have if x equals 0? We have 0 successes. Let's think back to algebra. What is anything raised to the 0 power? 1. So this is effectively right now 1 times 1. Are you guys with me so far? Perfect. Then we're going to use the probability of failure, and we're going to raise that to the power of the number of failures. So if the probability of success is 0.25, what's the probability of failure? 0.75, and I'm going to raise that to the number of failures. How many failures are there in each situation here? Well, there's 4 failures because they had to all fail for x to be 0, successes to be none. So really, in this particular problem, even though I know it was a lot of things to write down just to show you what the answer is, it's just 0.75 to the 4th power because it's 1 times 1 times 0.75 to the 4th power. So in these 4 children with a probability of success of 0.25 each time, what is the probability that none of them succeed? They all fail. 0.3, we're going to go 4 decimal places. 0.3164. Do you guys have any questions about that? Okay. What's the next question asking me? What's the probability that I have 1 success? Now, how could that happen? It could be the first kid is a success and then I have 3 failures. It could be that I have a failure, second kid is a success and then 2 failures. 2 failures, a success, and then a failure. 3 failures, and then that last kid comes in clutch. So how many different ways is it possible to get 1 success out of 4 kids? There are 4 combinations here. Probability of success. Each trial, the probability of success is 0.25. In this situation, how many successes are there in each of the groups? 1. And then what's probability of failure? 0.75. And how many failures are there? 3. So this one, you are going to do 4 times 0.25 times 0.75 to the 3rd power. This will be the probability that one of the 4 kids is a success, and I don't care which kid it is. And what's that probability? Perfect. Very good, very good, very good. Awesome. Next. What is this question asking? I get 2 successes. Which 2 are the successes? Doesn't matter. So how many different combinations are there that I get 2 of the 4 that are successful? Well, I could have 2 successes, then 2 failures. I could have a success, a failure. Or I could have a success, 2 failures, then a success. Those are all the different ways that the first kid is a success, and then one of the other 3 is a success. So it could be that the first kid's a failure, then a success, 2 in a row, then a failure. Could be failure, success, failure, success. These are the only other ways that the second kid could be the first success and then the rest. And then there's only one other option. Anybody know what it is? 2 failures, 2 successes. So, how many combinations are there here? 6. How many probabilities of success? How many probabilities of failure? There we go. 6 times 0.25 squared times 0.75 squared. This is the probability that 2 of the 4 kids have type O blood, and I don't care which ones. Who's having fun? Oh, I am. I'm having the best time, you guys. All right. How many different combinations are there for 3 of the 4 to be successful? Well, maybe I get 3 in a row, then a failure. Maybe I get 2, then a failure, then a success. Maybe I get 1, a failure, 2 successes, a failure, and then 3 successes. How many different combinations is that? 4. 0.25. What am I going to raise the 25% to? Power of 3. What are we going to raise the 0.75 to? Power of 1. All right, cool. So 4 times 0.25 to the 3rd power times 0.75. This is the best ever. Point who, what, when, where? Here we go. You guys, we only have 1 more left. Huh? You want me to do it? No. Got 1 more left. What's this one asking? Probability that we get 4 successes. How many different ways can we get 4 successes out of 4 kids? 1 way, you guys. It's that they are all type O. 1 way. So 0.25 is going to be raised to the power of 4. And technically speaking, 0.75 is raised to the power of 0. But what does that become? It really just becomes a 1. So technically speaking, you don't even have to type it in. You don't even have to type the first one. That's just a whole thing. And so, ladies and gentlemen, what is the probability that with a 25% chance per kid that all 4 have type O blood? Very good. Okay. Does anybody see a pattern? You should see a few patterns maybe. What do you notice? Yeah, you guys see this? 1, 4, 6, 4, 1. Any of you in pre-cal?
Pascal's triangle.
Anybody know what Pascal's triangle is?
Oh yeah, we're doing it now.
Yeah. If you're in pre-cal, you started Pascal's triangle today. Coincidence? 100%. This was totally a coincidence. I did not know until second period today when I started talking about this that they were like, oh, wait, we're doing this in pre-cal right now. This is totally a coincidence. This Pascal's triangle, you guys, is the first 4 or 5 lines. I guess 4, technically 5, whatever. It doesn't matter. These are the first few lines of Pascal's triangle. So you start with a 1, 1, 1, right? The outsides are always 1. And you add these 2 numbers to get the number that's in between them on the next line. So 1 and 1 is 2. 1 and 2 is 3. 2 and 1 is 3. 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4. Look at that line. Anybody notice something? 1, 4, 3, 4, 1. What the heck? What is going on here? Pascal's triangle is the triangle that gives you binomial coefficients. And what is the name of this distribution? The binomial distribution. Now, I tell you that just to say that it's kind of cool, and I'm a math nerd, so I wanted to show it to you. But I also say that to say that these number of combinations, you probably have done combinations and permutations, maybe, hopefully. If you haven't, it's not a big deal. I don't want you to get too tied up in it. Pascal's triangle does not show up on our test, okay? However, knowing how to find the binomial coefficient might. So we will talk about how to do that. Notice that the probability of success and then the probability of failure and the exponents. What do the exponents always add up to? 4, the number of trials, okay? So because if I'm going to have n number of trials, then I'm going to have success and then the complement of success for the failures. Everybody got it? All right, cool. So now we just need to make the probability distribution, and then we'll be almost done. We're super close. Don't quit on me yet. But we're going to make the probability distribution for this setting. Here it is. We have x and the probability of x, and we are making the probability distribution, which basically just means we are putting all of our data that we just did, all of our probabilities, we're putting them into this chart. Probability that x equals 0, no successes, was 0.3164. 1 was 0.4219. I'll stop saying numbers so you don't write down the wrong ones. Cool. Now, what if I asked you guys to find the mean and the standard deviation of this distribution? Could you do it now?
Yeah.
How? L1, L2, let's go, stat calc 1, all the fun things, right? I am not going to ask you to do it. You're so welcome. Okay? But you could, right? You could. Okay, cool. Any questions? Nope, we're going to write down the formula first, and then we'll be done. We're just going to write down our formula here.
What?
I know. It's a big week this week. Okay, so here's what we wrote down a few minutes ago. The probability that x equals some number of successes was equal to the number of combos times the probability of success raised to the number of successes, and then the probability of failure raised to the number of failures. Okay? And you guys all just did 5 problems. X equals 0, 1, 2, 3, and 4. You did 5 problems using that formula. Do you agree with me? Then don't freak out when I write the formula in mathematical notation, because you already did it. It's already easy, right? Here it is. The probability that x equals little x. Now, what's that little x? This little x is the number of success. Very good. Woo! Look at us. All right. Here's the part of the formula that everybody goes, what? This was on your diagnostic quiz on the second day of school or whatever it was. N choose X. So, for those of you who have taken pre-cal in the past or are currently in pre-cal, you would use the NCR function on your calculator. N choose R on your calculator. N is your number of trials, R or X. Pre-cal uses R, stats uses X. X is your number of successes, or R is your number of successes. This tells you the number of combinations, okay? So your calculator does it for you. It's under math and probability. If you go to math and probability, you'll see NCR. If you go to NCR, the only problem is that if you have one of the yellow older calculators, you have to put the N in first, then you go to math probability NCR, then you put in the R or the X. If you have one of the newer ones, you can actually go back and forth in order to put it in, okay? But, for example, if you want to know what is 4 choose 2, meaning 4 trials with 2 successes. You would put in a 4, you would go to Math PRB, NCR, and you'd hit enter, and then you'd put a 2. And when you hit enter, what do you get? 6, because that's the number of combinations.
Wait, NPR?
NCR, NCR. This is the number of combinations. The P is if you're doing a permutation. We don't really do permutations. Okay, so there's that. Probability of success. We use a P for that notation, a lowercase p. The number of successes we've already defined is x, so it's p to the x power. Now, probability of failure. If the probability of success is p, how can I write the probability of failure in notation form? It is the complement, so 1 minus p. Because if the probability of success is 0.25, the probability of failure is 1 minus 0.25. And then the number of failures. How can I use what notation I already have to get the number of failures?
Big X minus little x.
Ah, close. N is my number of trials minus X is my number of successes. That tells me how many failures I have. So just to clarify here, N is the number of trials. And so N minus X, if I have N trials and I take away the number of successes, I'm obviously left with the number of failures. Here's the great news, you guys. I have really great news for you. This formula is on the formula chart. However, it doesn't say it in words. It says it in this notation format. But I have even more great news for you.
Can you tell us?
Come back tomorrow and I'll tell you.